Hello friends, I Deepak Prajapati welcome you in lecture number 10 on random variables. Today we are going to discuss about cumulative distribution function of a continuous random variable. We have discussed cumulative distribution function for discrete random variable in our previous lectures. So today we are going to define the same thing for continuous random variable. So before going for continuous random variable, we just recall that if capital X is a discrete random variable, then the cumulative distribution function capital F of X is given by probability that capital X is less than or equal to small x, and this is defined for each real number capital X. So this we have defined for discrete random variable. Now for continuous random variable also the definition is same. The only difference is for discrete random variable this is given by summation of probabilities, summation of values of probability mass function where y is less than or equal to small x. So this is for discrete random variable, and for continuous random variable this summation is going to be replaced by integrals. So let us see what is CDF for a continuous random variable. Capital X is a continuous random variable with probability density function f of x. Then the cumulative distribution function of capital X is denoted by capital F of x and is defined as fx equal to probability that x is less than or equal to x, and this is nothing but integral of probability density function with limit minus infinity to x, and this is defined for each real number x. So if I want to find out, suppose I want to find out f of 3, then this is going to be integral of probability density function with limit minus infinity to 3. So in this way we can find out value of cumulative distribution function at each real number by this formula, and this is simple integration. If we know the formula for PDF, we can find out this value of CDF at each and every point. Now we know that the integral, this definite integral represents the area under the curve of probability density function known as density curve. Okay, so here we have shown it geometrically. Suppose this is the density curve, and on x-axis we consider values of random variable, and on y-axis we consider values of probability density function. Now if I want to find out value of CDF, cumulative distribution function, at any point A, then by definition f of A is nothing but probability that capital X is less than or equal to small a, and this is nothing but by definition of CDF integral from minus infinity to a f of x dx, and this integral represents the area under the graph of fx between minus infinity to a. So we have to consider this shaded area which I have shaded by these blue lines. So this shaded area is nothing but value of cumulative distribution function at point A. So this is the geometrical meaning of cumulative distribution function of a random variable. So if we can find out value of this area or if we are able to integrate this function, we are able to find out value of CDF at point A. So in this way, for each real number x, fx is the area under the density curve to the left of x. So here we are interested in f of a. So f of a is the area under this density curve which is to the left of this small a. So let us make some notes. Suppose x is a continuous random variable with probability density function small fx and cumulative distribution function capital F of x. Then for any number a, we can find out probability that capital X greater than a by this formula 1 minus f of a. Probability that capital X is greater than a is given by 1 minus value of distribution function at x equal to a. So we can understand this from this figure also. Suppose this is the graph of probability density function of a random variable capital X, and suppose this point is small a. So the area to the right of a is given by probability that capital X is greater than a, and as we discussed, the area to the left of a is nothing but probability that capital X is less than or equal to a, and which is by definition of CDF, which is equal to f of a. And we know that if I consider these two events, capital X greater than a and capital X less than or equal to a, for any real number, if we consider these two events, capital X greater than a and capital X less than or equal to a, then both the events are mutually exclusive. That means their intersection is empty and they are exhaustive, means their union is the whole sample space. So using this fact, if I consider probability of union of these two events, that is equal to probability of sample space, and because these two are mutually exclusive, probability of their union is nothing but sum of their probabilities. So probability of union of these two events equal to probability that x is greater than a plus probability that x is less than or equal to a, and probability of sample space is always 1. So from this we obtain that probability that capital X is greater than a is given by 1 minus probability that capital X is less than or equal to a, and this is by definition, this is nothing but value of CDF at x equal to a. So in this way we can find out this type of probability. Probability that capital X is greater than a is given by 1 minus value of CDF at x equal to a. And this is obvious from this figure also. If we are interested in this probability that x is greater than a, if we are interested in this area, then this area is nothing but the whole area minus this area to the left of a. So the area under the whole curve is 1. So this area, probability that x is greater than a, is nothing but 1 minus this area to the left of a. Area to the right of a is nothing but total area minus area to the left of a, and area to the left of a is nothing but small capital F of a, and total area is 1. Another important remark, if we take any two real numbers a and b where a is less than b, then probability of event that capital X lies between a and b is given by f of b minus f of a. So this also we can understand from this figure. If I consider this event capital A less than or equal to x less than or equal to b, then probability of this event is nothing but this shaded area. Now if you observe this thing, if I consider this event capital X less than or equal to B, then this I can write as union of these two events, capital X less than or equal to A, or I can take strictly less than A. Capital X less than A union this event A less than or equal to capital X less than or equal to B. Capital X less than or equal to B means we have to go up to B. This represents the left hand side of B starting from minus infinity. So that I can write as, so we can understand in this way also. Suppose I have AB and this one. So if I consider this part minus infinity to B, then it is nothing but union of these two parts up to A, that is capital X is less than A union A less than or equal to capital X less than or equal to B. So this portion is here and this one is this part. So capital X less than or equal to B is nothing but union of two mutually exclusive events. So capital X less than or equal to B is union of these two events, and these two are mutually exclusive. That means their intersection is empty set. So therefore probability of capital X less than or equal to B is nothing but sum of probabilities of these two events. So probability that A less than or equal to X less than or equal to B equal to probability that X is less than or equal to B minus probability that X is less than A, and this is nothing but capital F of B minus capital F of A, because we know that probability that capital X equal to A is always 0. Okay, so whether I write X less than or equal to A or X is less than A, both are the same thing for continuous random variable. Okay, so in this way we obtain this important remark: probability that capital X is in between A and B is given by value of CDF at B minus value of CDF at point A. So we have made two important remarks. If A is any real number, then probability that X is greater than A is given by 1 minus value of CDF at point A. And another remark is probability that capital X lies between A and B. This we can directly find as value of CDF at right hand point minus value of CDF at left hand point of the interval. So let us consider one example. In this example we will see how to write down cumulative distribution function from a given probability density function, and we will use that CDF to calculate some probabilities. So let us take this example number 1. Suppose the probability density function of the magnitude x of a dynamic load on a bridge, which is measured in newtons. Dynamic load is measured in newtons, is given by fx equal to 1 by 8 plus 3x by 8 when x lies between 0 and 2. Okay, or this we can write as when x is in close interval 0 to 2. Okay, or 0 less than or equal to x less than or equal to 2, and value of PDF is 0 otherwise. That means if x is outside this closed interval. So we have to find the cumulative distribution function of x. Also we have to find the probability that the load is between 1 and 1.5, and also the probability that load exceeds 1. Okay, so probability that load lies between 1 and 1.5, that means P of 1 less than or equal to capital X less than or equal to 1.5. Here capital X is the random variable which represents dynamic load on a breeze, and the probability that load exceeds 1 is given by probability that capital X is greater than 1. So before going for these probabilities, first we find out cumulative distribution function. So to find out cumulative distribution function, we first concentrate on this probability density function. So function is non-zero in closed interval 0 to 2, and outside this interval function is 0. Suppose this is 0 and this is 2. Now we will consider, instead of f of x, we will consider this definition. We will use dummy variable as small a. Instead of small x, we will use small a as dummy variable. So we will use this f of a equal to probability that capital X is less than or equal to a, where a is any real number. So instead of small x, we are using small a. It is dummy variable. You can use any other variable also. Now here, if we want to find out value of CDF at any real number a, then there are three possibilities. Either number a lies in between 0 and 2, it is outside this interval, it can be on the right hand side of 2, or it can be on the left hand side of this 0. So there are three cases we have to take into consideration. We have three possibilities. If I want to find out value of CDF at any real number a, then a can be strictly less than 0, a can be in between 0 and 2, and a can be greater than 2. So in all the three cases, we have to write down value of CDF. So first we start by taking a negative, that is a less than 0. Now if a is less than 0, then by definition f of a is probability that capital X is less than or equal to a. This is again integral from minus infinity to a fx dx. Now a is negative, and here we are integrating with respect to x from minus infinity to a. So here x is less than or equal to a. In this integral, the variable of integration is small x. So in this integral, small x is less than or equal to a, but a is negative. Therefore x is also negative. And if x is negative, value of probability density function is 0. You can see here. If x is outside 0, 2, then value of CDF is 0. So therefore we can put 0 here, and the integral of 0 is 0. So if a is negative, then value of CDF is 0. So what we obtain, f of a equal to 0 if a is strictly less than 0. Another possibility, suppose a is between 0 and 2. So you can see I have sketched the graph of probability density function. Probability density function is represented by straight line between 0 and 2. So we can easily sketch the graph. To sketch the straight line, we require 2 points on the straight line. So if I put x equal to 0, I will obtain 1 by 8. That means at x equal to 0, value of fx is 1 by 8. And similarly, if I put x equal to 2 here, I will obtain 1 by 8 plus 6 by 8, that is 7 by 8. So at x equal to 2, value of function is 7 by 8. So that we can put here at x equal to 2, value is 7 by 8. And then we join these 2 points to sketch the graph of PDF. Now if x is negative, value of CDF is 0. And if x is positive, f is greater than 2, then also value of PDF is given to be 0. So outside this interval, value of PDF is 0. Okay, so that we can represent in this way by arrow. Okay, the points are on the x-axis because fx is 0. Now we are interested in finding out value of cumulative distribution function at point A if A is in between 0 and 2. So we assume that suppose A is somewhere here. It can be anywhere in between 0 and 2. So suppose A is somewhere here. So by the definition, if I consider f of A, then I have to take integral of fx up to A. So that is minus infinity to A by the definition. Now A is in closed interval 0 to 2. So you can see up to this point value of fx is 0 and after this point it changes. So we break our integral into 2 parts. Our integral is minus infinity to A fx dx. Okay, this one. My f of A equal to minus infinity to A fx dx. Now we can see value of PDF is 0 up to x equal to 0, and then if x is in between 0 and 2, it is given by this straight line. So this we have to break into 2 parts, minus infinity to 0 plus 0 to A. So that is what I have written here, minus infinity to 0 fx dx plus 0 to A fx dx. Now in this part, x is negative, x is strictly less than 0. So fx is going to be 0. So this term is going to be 0 because fx is 0 if x is negative, and in this integral x is negative. So this is going to be 0. And we are left with integral from 0 to A fx dx. So that means x is in between 0 and A. If I concentrate on this integral, then x is less than A and A is in between 0 and 2. A is between 0 and 2. Therefore, x is also in between 0 and 2. And if x is in between 0 and 2, fx is given as 1 by 8 plus 3x by 8. So we put value of fx there. So here we put 1 by 8 plus 3x by 8. Now this is simple integral. Integral of 1 by 8 is x by 8 plus this is going to be x square by 2. So it is 3x square by 16. And x is having limits 0 to A. So if we put x equal to A, we obtain A by 8 plus 3a square by 16. So f of A is given by A by 8 plus 3a square by 16 whenever A is in between 0 and 2. Last case is if A is strictly greater than 2. So A is somewhere on the right hand side of 2. So again we go by definition, f of A is minus infinity to A fx dx. So I have to include up to minus infinity to A. So this I can rewrite as minus infinity to 2 and 2 to A. Minus infinity to 2 fx dx plus 2 to A fx dx. But this is nothing but probability that capital X is less than or equal to 2. And if x is greater than 2, then fx is 0. So if I consider integral of fx from 2 to A, then x is greater than 2, therefore fx is 0, and therefore this integral is 0. Now this is nothing but f of 2, and in earlier case we have seen that f of a is given by a by 8 plus 3a square by 16 for every a between 0 and 2. So we can find out f of 2 by putting a equal to 2 here. Okay, so a equal to 2 means 2 by 8 plus 3 into 4 by 16, that is 12 by 16. And after simplification we obtain f of a equal to 1. So f of a is 1 if a is greater than 2. And f of a is given by a by 8 plus 3a square by 16 whenever a is in between 0 and 2. And if a is negative, f of a is 0. First case. So if we combine all these cases, we obtain the formula for CDF. The cumulative distribution function is given by 0 if a is negative, a by 8 plus 3a square by 16 if a lies in between 0 and 2, and 1 if a is greater than 2. Now here a is dummy variable, we can replace small a by small x also to write fx in terms of x. So this is the cumulative distribution function of a given random variable. Now if I want to find out the probability that the load is between 1 and 1.5, so it is given by probability that 1 less than or equal to x less than or equal to 1.5, and this is using that property we just showed, that probability that x is in between a and b. This is given by capital F of b minus capital F of a. So here we put f of 1.5 minus f of 1, and this we can calculate from this. F of 1.5 means it is in between 0 and 2, so we put x equal to 1.5 here. Similarly, f of 1 can also be calculated from this by taking x equal to 1. So first we put x equal to 1, and then we put x equal to, first we put x equal to 1.5 and then x equal to 1. So after simplification, this is 19 by 64. Similarly, the probability that load exceeds 1 is given by probability that capital X greater than 1 is nothing but 1 minus probability that x is less than or equal to 1. Okay, again these two are disjoint events. Okay, so using complementary events. Now this is nothing but capital F of 1. So after putting x equal to 1, in definition of f of x, here we put x equal to 1. So 1 by 8 plus 3 by 16. So it is 11 by 16. So in this way we can decide the cumulative distribution function of a continuous random variable if formula for PDF is given. So in the next lecture we will do some more problems on cumulative distribution function of a continuous random variable. I hope you like this lecture. Thank you very much.